Today, we will talk about the gyroscopic system, which is used in some of the basic flight instruments, also known as the six-pack. As we know from previous videos, the airspeed indicator, the altimeter, and the vertical speed indicator use air pressure to give their indications by means of the pitot static system. While on the other hand, the attitude indicator, the heading indicator, and the turn coordinator use gyroscopic principles to give their readings by means of the gyroscopic system, which we will discuss in this video. With this in mind, we must say that each of these instruments has its own internal gyroscope, specially arranged to measure a certain parameter. But before we go into detail with each one, let's see what a gyroscope actually is. A gyroscope, often abbreviated as a gyro, is any symmetrical body rotating at a speed sufficient to experience the gyroscopic effects. This is a very basic description. Since according to this, we could say that a bicycle wheel, a propeller, or a dedicated gyro are all examples of gyroscopes. As we can see then, the design of a gyro can vary greatly depending on its use and application. However, they all have some components and characteristics in common. In essence, every gyroscope is composed of a rotor that spins at a high speed, the spin axis of the rotor, one or more gimbals, and the frame that supports the gyro. This particular design allows the gyro to have freedom of movement on all three axes, and therefore it is known as a free gyro. Now, when the rotor is not moving, nothing happens, and the gyro behaves like an ordinary object. However, when it starts spinning, it begins to experience the gyroscopic effects. These effects are rigidity in space and precession. Let's take a closer look at each of these, starting with rigidity in space. This establishes that when the rotor of the gyro spins, it remains in a fixed position in its plane of rotation, regardless of the movement of the gimbals or the frame, as we can see in this example. Here, although the gimbals and frame move, the rotor remains rigid in space. We can better appreciate this effect with this other example. Here, as we can see, independently of the movement of the frame or the gimbals, the rotor maintains its axis of rotation rigid in space. Now, the degree of rigidity of the gyroscope is directly proportional to its rotational speed, or RPM, and its moment of inertia. This means that the faster the rotation of the gyro, the greater the rigidity in space and vice versa. We can even experience this in everyday life when riding a bicycle. Since in this case, if we ride the bicycle at a low speed, the wheels will spin slowly, which means that they will present less rigidity in space, and therefore the bicycle will be less stable. On the other hand, if we ride the bicycle at a higher speed, the wheels will spin faster, and therefore they will present more rigidity in space, making the bicycle more stable. Now, the other factor that affects the rigidity in space is the moment of inertia. Basically, this means that the greater the mass and effective radius of the rotor, the greater the rigidity in space and vice versa. As we can see in this example, the mass of the rotor is concentrated in the outer part. Because if we want to obtain the highest moment of inertia, the mass should be located as far away from the axis of rotation as possible. In other words, the larger and heavier the gyro rotor is, the more rigidity in space it will have. This can also be experienced on a bicycle, because if we ride a bicycle with small wheels, they will present less rigidity in space, and therefore less stability. While if we ride a bicycle with bigger wheels, they will present more rigidity in space, and therefore the bicycle will be more stable. In general terms, we can say that the gyroscopes installed in aircraft instruments spin at about 18,000 RPM, have an effective radius of about 2 centimeters, and are heavy. Therefore, we can expect this type of gyros to have a high rigidity in space. With this being said, let's continue with the other gyroscopic effect. The precession. This establishes that any force applied perpendicularly on the plane of rotation of a gyro will be exerted at 90 degrees in the direction of rotation. This may sound a bit complex so far, but let's take a look at a couple of practical examples. In the right side we have a rotating disc, which will represent the gyro. Now, let's suppose we apply a force at this point. According to the precession effect then, this force will actually be exerted at 90 degrees in the direction of rotation, it is, at this other point, which will cause the disc to tilt in this way. Let's look at another example. Here we have a gyro with its axis of rotation positioned horizontally. Now let's suppose that we apply a force at this point. Due to precession, this force will actually be applied 90 degrees in the direction of rotation. It is, in this other point, which will cause the gyro to tilt this way. Now, we have to mention that the magnitude of the precession is directly proportional to the applied force and inversely proportional to the rotational speed. This means that the faster the rotation of the gyro, the smaller the precession and vice versa. And on the other hand, the greater the force applied to the gyro, the greater the precession and vice versa. Up to this point we have already explained what the two main gyroscopic effects are. Now let's see what are the different types of gyroscopes we can find. In essence, gyroscopes can be classified into displacement gyros and rate gyros. And at the same time, displacement gyros can be divided into free gyros and tied gyros, among which we can highlight the earth gyros. Let's see a brief description of each one of these and where they are used, starting with the displacement gyros. Let's start with the free gyro, also known as space gyro. This is a gyroscope with 3 degrees of freedom, which means that it can rotate freely around the 3 axes. And although it is the most widely used to explain the gyroscopic effects, in terms of practical applications in aviation, they are only used in the older inertial reference systems. Let's now move on to the next type of gyro. The tied gyro. This gyro also has 3 degrees of freedom, however it incorporates a control system that keeps the axis of rotation in a particular position. An example of this type of gyro is the one found in the heading indicator. In this case, it keeps the axis of rotation aligned with the yawing plane of the aircraft in order to give an adequate heading indication. Now, a similar variant of this tied gyro is the earth gyro. The particularity of this gyro is that it incorporates a control system that uses the Earth's gravity to maintain the axis of rotation in a particular position. This type of gyro can be found, for example, in the attitude indicator. In this case, it keeps the axis of rotation perpendicular to the horizon in order to give an adequate attitude indication. With this, we have already seen the displacement gyros. Let's continue with the rate gyros. Basically, a rate gyro only has 2 degrees of freedom, which means that it is restricted in one of the axes. So when it attempts to rotate in the plane that is constrained, the gyroscope will precess, which can be measured by a spring system, to obtain the rate of angular variation. This type of gyro can be found, for example, in the turn coordinator, where it is used to measure the rate of turn, or in other words, how fast the aircraft is changing its heading. In upcoming videos, we will look in more detail at the exact principle of operation of the gyroscope of each instrument. So with this being said, let's look at the different systems that can be used to spin the instrument gyros. In aviation, gyros can be driven by electricity or by air. In the electrical system, it is most common to use direct current. And in the air system, either vacuum suction or positive air pressure can be used. Normally, most light aircraft have the following configuration. The attitude indicator and the heading indicator are driven by an air vacuum pump, while the turn coordinator is driven by the electrical system of the aircraft. The main objective of this design is that in the event of a failure in one of the systems, not all gyro instruments are affected. Finally, let's see what practical applications gyros have in aviation. We have already mentioned that lighter and simpler aircraft use gyros in some of the basic flight instruments. However, in the most complex and modern aircraft we can find gyros in other systems such as the gyromagnetic compass, the inertial navigation and reference systems, the yaw damper, the autopilot, among others. I hope the information presented in this video was useful. If so, don't forget to share, like, subscribe, and leave a comment down below. Thanks for watching.